Hello everyone. So in this class we are discussing the frequency response plots. In the control system designing, the most important parameter is stability. So in order to find out the stability of a system in terms of its frequency, we are having some frequency response plots such as Bode plots, polar plots, and Nyquist plots. So in this class we will see the Bode plot, what is the basic procedure to plot, what are the steps you have to follow, and how to find out the stability of a system with respect to this model plot. Okay, Bode plot. So Bode plot is a frequency domain technique in which magnitude and phase are drawn one below the other. So what it means that Bode plot consisting of the two response plots. What are the two response plots? Magnitude plot and phase plot. So frequency response means immediately we'll get into one point. So it consisting of the magnitude as well as the phase. So here we can draw the magnitude plot as a function of frequency as well as the phase angle as a function of frequency. So Bode plot consisting of the two graphs, magnitude plot as well as phase plot. So for example, if you are taking one loop, open loop transfer function, g of s equal to k into 1 plus st1 divided by s into 1 plus st2 and 1 plus st3. So then the basic first step while you are plotting this Bode plot, we need to convert the given transfer function into the frequency domain. How it we have to convert that means just by assuming s equivalent to j omega. Just by letting s equivalent to j omega, we will convert the given transfer function into the frequency term. So that is g of j omega equivalent to k into 1 plus j omega t1, 1 plus j divided by j omega, one second, k into 1 plus j omega t1 divided by j omega into 1 plus j omega t2, 1 plus j omega t3. So that is the first step, converting S domain into the frequency domain just by letting S equivalent to j omega. And then we need to write every product term as a combination of its magnitude and the phase. So that is for the first term k at an angle of 0 degrees. So and the second term 1 plus j omega t1. So how we can write the magnitude for this term? Magnitude of this one is square root of 1 plus omega square t1 square. And phase angle. How to write the phase angle? Tan inverse of imaginary part by real part. What is the imaginary part here? Omega t1. Real part is 1. So omega t1 by 1. So we will get the tan inverse of omega t1 divided by, and magnitude is for this j omega term omega, and phase angle for this term is 90 degrees. So please remember, if the product term is a purely imaginary and the phase angle is always 90 degrees. Why? Because what is the phase angle? How to calculate? Tan inverse of imaginary part by real part. What is the imaginary part here? Omega. What is the real part? 0. So something by 0, what we will get? Tan inverse of infinity. When we will get the infinity? And the angle is 90 degrees. So that's why for a imaginary part, the phase angle is always 90 degrees. What about the real part? Real part, the phase angle is always 0 degrees. And then next this term, how we can write this term? Square root of 1 plus omega square t2 square, and that phase angle is tan inverse of omega t2. And then third term, 1 plus omega square t3 square and tan inverse of omega t2. Okay. So in this way, we have to write every product term as a combination of its magnitude and the phase angle. So then from this, we will separate the magnitude and separate the phase angle. What are the magnitude terms here? K, 1 plus square root of 1 plus omega square t1 square, 1 plus omega square t2 square, and then 1 plus omega square t3 square. And the phase angles. What are the phase angles here? 0 degrees, so there is no value for that. So directly I'm writing tan inverse of omega t1 minus. So take these angles from the denominator to the numerator so that we will get the negative sign. So minus 90 degrees minus tan inverse of omega t2 and minus tan inverse of omega t3. Okay. Now we will substitute omega value from 0 to infinity because the frequency will be varying from 0 to infinity. Then what is the corresponding magnitude we had to calculate? Similarly, by changing the frequency value from 0 to infinity, what is the corresponding phase angle we need to calculate? So two plots separately we need to find out. But see here, the magnitude is in the form of product terms, right? So instead of calculating this magnitude directly, so if you are converting these terms into the logarithmics, so just by taking the logarithmics for that, so that it's easy to find out the magnitude response. Why? Because while you are taking the magnitude term, so the magnitude of product terms will become the summing terms. It is easy to find out that addition instead of multiplication. So for the reason, instead of calculating this magnitude directly, we will take into that in the logarithmic terms. So just by taking that 20 log on both sides, so how we can write? So 20 log of g j omega equivalent to, so write 20 log of k by, sorry, 1 second, 20 by 20 by 20 by 1 plus 1 plus omega square t1 square, omega into 1 plus omega square t2 square, 1 plus omega square t3 square. So write separately every term, k into 1 plus omega t1 into 1 by omega square t2 square into 1 by omega square t3 square. And by applying logarithmics on every term, so we'll get 20 log k by omega plus 20 log square root of 1 plus omega square t1 square minus 20 log 1 plus omega square t2 square minus 20 log omega square t3 square. See that previously it is in the product term, but now by converting into the logarithmics, so it will be coming into that addition. So addition is somewhat simple compared to the multiplication, right? So for the purpose, and it is easy to draw that magnitude in terms of logarithmics. So these are the basics procedure while we are converting magnitude into that magnitude in terms of logarithmics. And before going to draw the Bode plots, and just remember, so this Bode plot is an approximation plot. Why I will say that approximation plot means, so just by knowing that what are the given product terms, with that help of the product terms, directly you can be able to draw the its magnitude response. So how we can draw this? So let's see. If you are considering any transfer function, so the transfer function basically consisting of that any one of these following product term. Either it is a constant term, or either it is an integral factor, or either it is a derivative factor, or either it is a first order in the denominator, or first order in the numerator, or quadratic factor in the denominator, or quadratic factor in the numerator. So these are the terms we will observe in that any given transfer function. Okay. So if you know that how to draw the how to find out the magnitude for individual factor, so that if I suppose if I know the what is the magnitude response, so what is the magnitude of this integral factor and derivative factor or first order factor. So then I can simply add every term, every magnitude so that I will get the final value instead of calculating everything, right? So that's the reason. So first we have to know what the magnitude and corresponding phase values for every individual factor so that it is easy to calculate it. Yes. Okay. So please remember these are the basic factors we can observe in any given transfer function. So let's see that the first one, constant gain. So for example, if the transfer function g of s equivalent to consisting of only constant terms like 5, 10, 15 like that. So what is the magnitude and what is the phase for the given transfer function means? So already said, what is the first basic step? We need to convert the given transfer function into the frequency domain. just by putting S equivalent to j omega. So G of j omega equivalent to, so here it is only the real part, so there is no matter for that. So directly I'm writing K. So what is the magnitude of this K? So square root of K square. So square root of K square. So this square and root get cancelled, we will get that only. And what is the phase angle for the real terms? Always so 0 degrees. So that is K at an angle of 0 degrees. Okay. If I take the magnitude in terms of logarithmics, so what you can write? So 20 log of K, right? And what is the phase angle for these real terms? Always it is 0 degrees. For example, if you draw the magnitude plot with respect to the frequency, and the magnitude will be taken in terms of decibels. For example, if the k value is positive, k value equivalent to 1 exactly, k value equivalent to 1. So what is the value of 20 log 1? 20 log 1 value is 0, right? So if the k value is equivalent to 1, then the magnitude is in the 0 decibels. And if the k value is greater than 1, so then we will get the some positive value. And if the k value lies between 0 to 1, so then we will get the some negative decibel values. Okay, so that is k equivalent to 1, magnitude is 0 decibels, k value is positive 2, we will get the some positive decibels, and the k value is in between 0 to 1, then we will get the minus decibels. And what is the phase angle? Phase angle is even the omega value is varying from 0 to infinity also, the magnitude, the phase value is always 0 degrees. Okay, so in this way, we are going to calculate the frequency response of the given system for the constant factor. Next, let's see that second one, integral factor. What is the integral factor means? Generally, it is in the form of 1 by s. So 1 by s means it's corresponding to the integral factor, right? So let us take in one small example. G of s equivalent to k by s. G of s equal to k by s. K by s. Again, first we need to convert s domain into frequency domain. So g of j omega equivalent to k by j omega. So that is k by. So write separately. It's a magnitude and phase angle. So what is the magnitude of this term? So k by omega. And what is the phase angle? For the k value, it is the real value, right? So real value phase angle is always 0 degrees. In the denominator, it is only the imaginary term, purely imaginary term. What is the phase angle for the imaginary terms? 90 degrees. But it is in the denominator. So if I am taking it to the numerator, what it will becomes minus 90 degrees. Minus 90 degrees. So what is the corresponding magnitude? K by omega, and the phase angle is minus 90 degrees. If you're writing the magnitude in terms of decibels, so how we can write 20 log of k by omega. And what is the phase angle? Minus 90 degrees. Minus 90 degrees, right? What it means that if you're having any integral factor, if you're plotting the phase response, if the frequency value will be varying from 0 to infinity, but the phase angle is always minus 90 degrees only for the integral factor. Okay, keep it in mind. The phase angle is fixed, always minus 90 degrees. Let's see the magnitude plot. For example, if you are substituting the frequency omega value is equivalent to 0.1k, 0.1k. What's the magnitude function here? 20 log k by omega. So now what is the value of omega? 0.1k. So that is k get cancelled, you will get the 1 by zero point 0.1. So what is the value of 1 by zero point 0.1? It is a 10. What is the value of 20 log 10? So what we will get? It's a 20 decibels, right? Next, if you are substituting omega value equivalent to k, then 20 log of k by k. So k get cancelled. So what you will get the remaining term? 1. What is the value of 20 log 1? It is 0 decibels. Next, if you are taking the omega value equivalent to 10k, so that is k by 10k. So k get cancelled. You will get the 1 by 10. So how we are writing 1 by 10? 10 power minus 1, right? So if I take the minus at the starting, so that is minus 20 log of 10. So then what is the value of that one? Minus 20 decibels. See? At initially 0.1 k, you will get the plus 20 decibels. At the value of k, you will get the value of 0 decibels. At the value of 10k, you will get the minus 20 decibels. Here, what I am taking the frequency range 0.1 k, k, 10k. That is a decibel value, decibels per decay. So per decay, how much magnitude will be changed? So if you are plotting this response at 0.1 k, you will get the 20 decibels. At k, you will get the 0 decibels. At 10k, you will get the minus 20 k, minus 20 decibels. So if you are joining these lines, you will get the corresponding slope is this one. So here observe that how much value from 0.1 to 10k. So 20 decibels to minus 20 decibels. So here to here, what is the change? 20 0. How much? 20 decibels will be the change. And here to here, 0 to here, how much it is changed? Again 20. Is it rising or decaying? It's a decaying. How much amount of decaying? 20 decibels value will be decaying for every decay. So that means for any integral factor, the slope will be following a minus 20 decibels per decay. Okay, so please remember that point. If you are taking any integral factor, so integral factor always magnitude response of minus 20 decibels per decay, and the phase angle is always minus 90 degrees, minus 90 degrees. It is a fixed value. And then, for example, if I am having that k by s square, what it means that 1 by s into 1 by s. I am having 1 by s square term, or 1 by s cube term, or 1 by s power n term. Then what is the corresponding magnitude for magnitude and phase angle? So just you can multiply this magnitude and phase angle into n only. So that is the corresponding slope becomes minus 20 into n decibels per decay, and the phase angle is minus 90 into n. What it means that, for example, if you are having that k by s square, k by s square, how many times? Two times. Then what is the slope? Slope change. Already it is integral factor. Integral factor is minus 20 decibels per decade. But here how many times you are having? Two times. That means what is the slope change? Minus 20 into 2. So that is minus 40 decibels per decade is the slope change for an integral factor if the factor is k by s square. If it is k by s cube, minus 20 into 3. K by s power 4, minus 20 into 4. K by s power n, minus 20 into n decibels per decade. Right? And the phase angle also, minus 90 into n. How many value will we are having? So just we can multiply that one. And one more point. So if you are observing this integral factor having the magnitude slope from initial point to that end point with a slope change of minus 20 decibels per decade. Okay. Let's see the next one. Derivative factor. So if I'm taking that function is now, derivative factor means yes. So that is g of s equivalent to ks. I am taking the function now. So already know what is the first step? We will need to convert s domain into the frequency domain. So that is s equivalent to j omega. So we can write k into j omega. So what is the magnitude of this term? So k omega, and the phase angle is 90 degrees. So here we need to take separately k and j omega. But k is a constant, so that the phase angle for the constant is 0. So that there is no effect on that. And that it is only purely imaginary. So that's why phase angle is always 90 degrees. So right magnitude and phase. So what is the magnitude A equivalent to 20 log of k omega, and the phase angle is plus 90 degrees. So let's apply some values of frequency omega value. For example, if omega value is equivalent to 0.1 by k, okay, zero point 0.1 divided by k. So what you will get? K into 0.1 by k. So then, so k get cancelled. What is the remaining term? 20 log 0.1. So what is the value of 20 log 0.1? Minus 20. How we are getting minus 20? How we can write 0.1? 1 by 10. How we can again write 1 by 10? How we are writing? 10 power minus 1, right? So if I take this minus here, minus 20 log of 10. So that is minus 20 decibels you are getting. Next, if the omega value is equivalent to 1 by k, so kk get cancelled, omega value 1, so that becomes 20 log 1, so it will get in the 0 decibels. And omega value is 10 by k, so again kk get cancelled, we will get the 20 log of 10, so that the slope is plus 20 decibels. Okay. Then if you draw the magnitude curve, so at k omega value is 0.1 by k, you will get that minus 20 decibels. If k omega value is 1 by k, you will get the magnitude is 0 decibels. If the frequency is 10 by k, you will get that magnitude is plus 20 decibels, right? Again, what you are observing? So for every decay of frequency, the slope will be rising of plus 20 decibels. So that's why here we are writing that on the magnitude plot. So what is the slope? Plus 20 decibels per decade. Okay, plus 20 decibels per decade. What about the magnitude plot in terms of integral factor? For integral factor, magnitude plot is minus 20 decibels per decade, right? And what is about the phase angle? Even the frequency will be changing from 0 to infinity. The phase angle is always fixed, that is plus 90 degrees only. Okay. I hope you can get the difference between that integral factor and the derivative factor. For the integral factor, the slope is always minus 20 decibels per decade. Minus 20 decibels per decade. And for the derivative factor, the magnitude is always plus 20 decibels per decade. And the phase angle is minus 90. Here the phase angle is plus 90. Plus 90. Similarly, if you are having that the function is k into s power n, then what will get that slope? So 20 into n decibels per decade. Right? Phase angle is always 90 into n. Okay. And remember one more important point. While you are plotting the Bode plot, so these first three terms, either constant term or integral term or derivative factor, derivative term, will plays the major role while you are deciding the magnitude. So what is important means while we will solve the problem, we will see that clearly. Okay. So then the remaining parameters, first order and second order, we will see in the next class. Okay. Thank you.